Let's talk about one of the most fascinating and misunderstood capabilities in modern language models, in-context learning. It sounds simple on the surface. You show a model a few examples in the prompt, and it figures out the pattern. No updates, no weight changes, just the examples sitting there in the input, and somehow the model generalizes from them. But when you really dig into what's happening under the hood and how to design systems around it reliably, the topic gets surprisingly deep. And in senior AI engineering reviews, this comes up constantly because it touches inference architecture, cost, reliability, and system design all at once. So let's start with the basics. In-context learning is the model's ability to perform a new task based entirely on demonstrations provided in the prompt. You might give it 3 examples of customer emails labeled as urgent or not urgent, and then the model correctly labels a 4th email it's never seen. The key thing here is that nothing about the model's weight changes. The model's parameters are frozen. What changes is the input, and the model uses patterns it learned during pre-training, patterns about patterns, really, to figure out what you're asking it to do. This is genuinely different from traditional machine learning, where you need labeled data, a training loop, and an updated model checkpoint to adapt to a new task. In-context learning essentially hijacks the attention mechanism to perform a kind of rapid task inference. Researchers have proposed that it's behaving like an implicit gradient descent step, that the attention layers are approximating what a small number of gradient steps would do if you actually fine-tuned on those examples. The model isn't memorizing your examples. It's using them to infer a transformation function and applying that function to the new input. Now, why does this matter for system design? Because in-context learning is the primary mechanism behind most of what we call prompt engineering in production. When you build a RAG system, a classification pipeline, or an extraction workflow, you're almost always relying on in-context learning to teach the model your specific format and domain at inference time. So understanding its mechanics tells you how to structure your prompts, how many examples to include, what order to put them in, and when to fall back to fine-tuning. Let me walk through the core mechanics more concretely. The most important variable is example selection. This is huge and often underestimated. Random examples from your dataset are not optimal. What works best, consistently, is selecting examples that are semantically similar to the test input. If a user is asking about a refund for a software subscription, your few-shot examples should include similar software support scenarios, not random customer service exchanges. In production systems, this means you're often pairing in-context learning with a retrieval step. You have a library of labeled examples stored in a vector database, and at inference time, you fetch the top K most similar ones and inject them into the prompt. This approach, sometimes called retrieval-augmented few-shot learning, is noticeably more reliable than static prompts with hand-picked examples. Example ordering also matters, though the effect is model-dependent. Some models show recency bias. The examples closest to the actual query have disproportionate influence. Others show primacy effects. The safest practical rule is to put your most representative, cleanest examples last, just before the new input, and always end with a clear, consistent format cue. The number of examples is the other big lever. More is generally better, but with hard diminishing returns. Going from 0 shot to 1 shot is often a dramatic improvement. Going from 1 to 4 or 5 examples continues to help. Beyond about 8 to 10 examples, the gains flatten for most tasks.